In the last couple of videos, we talked about definite integrals. Well, we can also talk about indefinite integrals of vector functions. And just like with real valued functions, an indefinite integral of a vector valued function is just the general antiderivative of that function. And because we take derivatives component-wise, we're going to take antiderivatives component-wise as well. Okay. Let's just do an example. Let's suppose I wanted to find the general antiderivative of e to the t cosine t dt. Okay. Well, I can evaluate this component-wise. So I could say this is going to be the general antiderivative of e to the t, comma, the general antiderivative of cosine of t dt. Okay. That's, of course, going to be e to the t plus a constant, which I'm going to write as c1, comma, an antiderivative of cosine would be sine of t plus a constant, which I'm going to write as c2. Do not assume that you're getting the same constant of integration for each component function. Okay. You get a constant of integration for each component, but it's not necessarily the same. Now, I generally don't take the time to write out that I'm going to be integrating each function, each component function individually. Here's what I would probably actually do. I would just say, oh, an antiderivative of e to the t is e to the t. An antiderivative of cosine is sine plus a constant. Okay. But notice my plus c here is plus a vector c. This is equivalent to what I've done here. My vector c here would simply be c1, c2. The constant of integration I got when I integrated the x component, comma, the constant of integration I got when I integrated the y component. Okay. I kind of prefer this because I'm just writing plus an arbitrary constant. I'm not tempted here to think that that constant has to be something like 1, 1, 2, 2. It's just an arbitrary vector. The x and y components don't have to be the same. If I'm writing the individual constants of integration, I'm so used to writing just plus c, it's really tempting to write plus c, but then it looks like I have to have the same constant of integration in both terms, and I don't. Okay. So I generally prefer this, but either method is totally fine. We get the same thing either way. We're getting a family of functions, and it's all functions that are antiderivatives of the original function r of t. I want to just take a look at one application problem here. Let's suppose I have a velocity vector. So let's suppose that I know that v of t is e to the 2t t cubed. And let's suppose that I know that my position function at time 0 is 5, 2. So this is my velocity function, and this is my initial position. And I want to find r of t. I want to find the position function. So this is just an example of what we call an initial value problem. I know that since velocity is the derivative of position, position is going to be an antiderivative of the velocity. So we're going to integrate e to the 2t t cubed dt. When we do that, we're going to get initially the general antiderivative, which is a family of functions. Quick u sub here, I would get 1/2 e to the 2t, and then t to the 4th, over 4, plus c. Okay. Now, that plus c says I did not get the position function. I got a family of functions, one of which is the position function that I want. It wouldn't make sense to say, this is my position. I am exactly here, plus an arbitrary constant, which means I could be some arbitrary distance away in an arbitrary direction. That doesn't do a very good job of specifying my position. I want to have a specific vector for that c before I call this a position function. So that's where we use our initial condition. So I can say that 5, 2, well, that was my r of 0, but r of 0 is going to be what I get if I plug in 0. Now, if I plug in 0 here, I'm going to get 1/2 e to the 0, which is just 1/2. If I plug in 0 to that second component, I'm going to get 0, and then plus c. But now I can solve for c. I can say that c is just going to be 5, 2 minus 1/2 0, and so that's going to be 4.5 or 9/2, comma 2. Then I can put the pieces together so that my final answer would be that r of t is 1/2 e to the 2t, comma t to the 4th over 4, plus not an arbitrary constant, but this specific constant that I just found. And certainly if I wanted to do the vector addition and write that as a single vector, I could. If I want to keep it as a sum of two vectors, that's fine too. That's just a matter of personal preference.